Right now, as you are watching this, a storm system in the Atlantic Ocean is doing something that has meteorologists at NOAA's National Hurricane Center running their models on a continuous loop. Hurricane Valeria reached Category 5 status on July 26, 2026, after intensifying by 95 miles per hour in a single 36-hour window. That is not a misprint. 95 miles per hour of additional wind speed in 36 hours. Scientists have a clinical term for what just happened. They call it rapid intensification, and the threshold for that classification is a 35 miles per hour increase in 24 hours. Valeria surpassed that threshold by a factor of nearly 3. At the same time, Super Typhoon Halong is churning through the western Pacific with sustained winds already exceeding 165 miles per hour on a track toward the Philippines. The Arabian Sea, a basin that historically produced mild, short-lived storm systems, is generating its third cyclone of the 2026 season, a frequency that has prompted a formal review by the World Meteorological Organization. And NOAA published a research bulletin this week confirming that Gulf of Mexico sea surface temperatures as of July 25, 2026 have reached the highest levels ever recorded for this point in the hurricane season in 172 years of consistent measurement. 4 simultaneous developments across 4 ocean basins, each one significant on its own. Together, they are telling a specific and serious story about what the atmosphere is doing right now and what it is capable of producing before the season ends. And today we are going to break down exactly what is driving Valeria's unprecedented intensification, where the highest risk is concentrated along the American coastline, and whether what scientists are measuring in the Gulf right now means the worst is still ahead. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Have you ever been directly in the path of a hurricane, typhoon, or major tropical cyclone? Tell me where you were, what category it was, and what the night of landfall actually felt like from inside a structure. Thousands of you watching this right now have lived through something the rest of the audience can only see on a map. I always want to hear those accounts because they communicate something that wind speed numbers alone cannot. If you want to be the first to know every time NOAA issues a significant advisory update on Valeria or any developing storm system this season, subscribe to the channel right now. It is completely free. A thumbs up also helps this reach people in the storm's projected path who genuinely need to see it. Let us get 6,000 likes on this one. Now, let us get into what is actually happening to this storm. On July 22, 2026, what was then Tropical Storm Valeria was crossing the central Atlantic with sustained winds of 60 miles per hour. A significant but not unusual storm for this point in the Atlantic hurricane season. The National Hurricane Center's track forecast places it on a westward heading with a projected landfall somewhere along the northern Gulf Coast between 10 and 14 days out. Uncertainty in long-range forecasting is standard at that range. No evacuation orders, no emergency declarations, routine monitoring. What happened next is the event that has meteorologists rereading their own model output to confirm they are reading it correctly. Between July 22nd and July 26th, a period of 96 hours, Valeria went from 60 miles per hour to 185 miles per hour of sustained winds. That is a 125 miles per hour intensification in 4 days, with the sharpest acceleration occurring between July 24th and 25th, when the storm gained 95 miles per hour in 36 hours. And I want to be specific about what those numbers mean, because a lot of people see wind speed figures and cannot translate them into a physical reality. The Saffir-Simpson scale used by NOAA and most international agencies runs from Category 1 to Category 5. Category 1 begins at 74 miles per hour, enough to snap tree branches, damage roofs, and cut power for extended periods across affected areas. Category 3, at 111 to 129 miles per hour, produces devastating damage. Well-built frame homes can lose roofs, roads become impassable. Most of the area becomes uninhabitable for weeks to months. Category 5, the scale's upper bound, begins at 157 miles per hour. Above that threshold, catastrophic damage is essentially universal. Complete roof failures on well-built structures, total destruction of mobile homes, widespread power outages lasting weeks to months. The scale stops at Category 5, but storms do not. Valeria's current sustained wind speed of 185 miles per hour places it among the strongest landfalling storms ever observed in the Atlantic Basin. For reference, Hurricane Allen in 1990 reached 190 miles per hour in the open ocean, one of the highest Atlantic wind speeds ever recorded. Hurricane Wilma in 2005 produced the lowest barometric pressure ever measured in an Atlantic hurricane. Valeria is currently tracking to challenge both of those historical benchmarks. Now let me explain what caused this. Because the rapid intensification Valeria has undergone is not random. It is the product of three specific atmospheric and oceanic conditions converging simultaneously in the same location at the same time. First, ocean heat content. Valeria crossed directly over a region of the Atlantic where sea surface temperatures were running 2.4 degrees Celsius above the 20th century average for late July. Hurricanes are heat engines. They extract energy from warm ocean water through evaporation, pulling vast quantities of water vapor into the atmosphere, where it rises, condenses, and releases latent heat that fuels the storm's rotation. The warmer the water, the more energy available for extraction. 2.4 degrees of anomaly sounds small. In the thermodynamics of hurricane intensification, it is the difference between a storm that reaches Category 3 and a storm that reaches Category 5 before anyone is fully prepared. Second, low wind shear. Wind shear refers to the change in wind speed and direction with altitude. High wind shear acts like a physical force pulling a hurricane apart, disrupting the organized vertical structure that allows the storm to intensify. The atmosphere above Valeria's track has been characterized by exceptionally low wind shear for a 5-day window, allowing the storm's central convective structure to organize with almost no disruption. Third, the Gulf Loop Current. As Valeria crosses into the Gulf of Mexico, which its current track projects on or around July 30th, it will encounter the Loop Current, a warm water feature that penetrates deep into the Gulf from the Caribbean. Loop current water can reach ocean heat content values deep enough to sustain intensification, even as the storm's outflow disrupts the surface temperature directly beneath it. Hurricane Katrina fed on the loop current in the 24 hours before its August 29, 2005 landfall. So did Hurricane Rita just 3 weeks later. Dr. Carrie Emanuel, professor of atmospheric science at MIT and one of the world's foremost authorities on hurricane intensity, stated in a July 25th briefing to the National Hurricane Center, Valeria is encountering near-optimal conditions for continued intensification across the next 48 to 72 hours. The ocean heat content values in its projected track are the highest we have measured in the Gulf at this time of year in the observational record. The storm will encounter the loop current at full strength. The conditions are in place for Valeria to remain at or above Category 4 intensity at landfall. The Gulf Coast between Texas and the Florida Panhandle is currently under watch. And when you look at what a Category 4 or 5 hurricane at landfall actually does to a coastal city, the infrastructure failure, the storm surge, inundation, the displacement of populations, you begin to understand why the models running in Tampa, New Orleans, and Houston right now are not producing comfortable projections. New Orleans, 2005, the Netherlands, every year since 1953. Two societies. Two fundamentally different relationships with the same basic threat of catastrophic coastal flooding from extreme storm events. The contrast between what happened in New Orleans when Hurricane Katrina made landfall on August 29th, 2005, and what the Netherlands has engineered for itself since the North Sea flood of February 1st, 1953, teaches something essential about the real variable in storm disaster mortality. It is not the storm. It is what was built before the storm arrived. On August 29, 2005, Katrina came ashore as a Category 3 hurricane on the Saffir-Simpson scale, with sustained winds of 125 miles per hour. It had been a Category 5 storm in the Gulf, just as Valeria is now. Before weakening slightly in the final hours before landfall, the storm surge Katrina pushed into New Orleans, and coastal Mississippi ranged from 15 to 28 feet in the hardest hit areas. The levee system protecting New Orleans designed for a Category 3 storm, underfunded, incompletely maintained, and in several locations structurally compromised before Katrina ever arrived, failed at 53 locations. Approximately 80% of New Orleans flooded. The water in some neighborhoods reached the rooflines of single-story houses. 1,833 people died. 1.2 million people were permanently displaced. The largest domestic displacement event in American history since the Dust Bowl, the economic damage reached $125 billion in 2005 dollars. Entire communities simply ceased to exist as functioning places. For years, now read that back and hold the specific detail. The levee system was designed for a Category 3 storm. Katrina arrived as a Category 3 storm. And still, the system failed. Not because of bad luck, because of underfunding, deferred maintenance, and decades of inadequate investment in protecting one of America's most historically significant cities. Now go back exactly 52 years from Katrina to the North Sea flood of February 1st, 1953. A severe extratropical cyclone drove a storm surge up to 5.6 meters above normal tide levels along the Dutch coastline. The existing sea defenses, damaged and inadequately maintained in the post-World War II recovery period, failed at hundreds of locations. 1,836 people died. 27,000 animals drowned. 150,000 people were evacuated. 72,000 homes were damaged or destroyed. The Netherlands, a country where approximately 26% of the land area sits below sea level, faced an existential decision after 1953: accept recurring catastrophic flood losses as the permanent cost of living on the delta, or build the infrastructure to make that permanent cost impossible. The country chose to build. What followed was the Delta Works, a system of storm surge barriers, sluice gates, dikes, levees, and tidal control structures that took 44 years to complete and cost, in modern equivalent terms, over $5 billion. The crown jewel of the system, the Maaslandering in Rotterdam's waterway, is one of the largest moving structures on Earth. Its two curved steel arms, each the length of the Eiffel Tower laid on its side, swing closed across the shipping channel. Automatically, when storm surge forecasts exceed a defined threshold, the system was designed to protect against a storm that occurs statistically once every 10,000 years. And when you look at what a Category 4 or 5 hurricane at landfall actually does to a coastal city, the infrastructure failure, the storm surge, inundation, the displacement of populations, you begin to understand why the models running in Tampa, New Orleans, and Houston right now are not producing comfortable projections. New Orleans, 2005, the Netherlands, every year since 1953, two societies, two fundamentally different relationships with the same basic threat: catastrophic coastal flooding from extreme storm events. The contrast between what happened in New Orleans when Hurricane Katrina made landfall on August 29th, 2005, and what the Netherlands has engineered for itself since the North Sea flood of February 1st, 1953, teaches something essential about the real variable in storm disaster mortality. It is not the storm, it is what was built before the storm arrived. On August 29th, 2005, Katrina came ashore as a Category 3 hurricane on the Saffir-Simpson scale, with sustained winds of 125 miles per hour. It had been a Category 5 storm in the Gulf, just as Valeria is now. Before weakening slightly in the final hours before landfall, the storm surge Katrina, pushed into New Orleans and coastal Mississippi, ranged from 15 to 28 feet in the hardest hit areas. The levee system protecting New Orleans, designed for a Category 3 storm, underfunded, incompletely maintained, and in several locations structurally compromised before Katrina ever arrived, failed at 53 locations. Approximately 80% of New Orleans flooded. The water in some neighborhoods reached the roof lines of single-story houses. 1,833 people died. 1.2 million people were permanently displaced. The largest domestic displacement event in American history since the Dust Bowl, the economic damage reached $125 billion in 2005 dollars. Entire communities simply ceased to exist as functioning places. For years, now read that back and hold the specific detail, the levee system was designed for a Category 3 storm. Katrina arrived as a Category 3 storm, and still, the system failed. Not because of bad luck, because of underfunding, deferred maintenance, and decades of inadequate investment in protecting one of America's most historically significant cities. Now go back exactly 52 years from Katrina to the North Sea flood of February 1st, 1953. A severe extratropical cyclone drove a storm surge up to 5.6 meters above normal tide levels along the Dutch coastline. The existing sea defenses, damaged and inadequately maintained in the post-World War II recovery period, failed at hundreds of locations. 1,836 people died, 27,000 animals drowned, 150,000 people were evacuated. 72,000 homes were damaged or destroyed. The Netherlands, a country where approximately 26% of the land area sits below sea level, faced an existential decision after 1953: accept recurring catastrophic flood losses as the permanent cost of living on the delta, or build the infrastructure to make that permanent cost impossible. The country chose to build. What followed was the Delta Works, a system of storm surge barriers, sluice gates, dikes, levees, and tidal control structures that took 44 years to complete and cost, in modern equivalent terms, over $5 billion. The crown jewel of the system, the Meeslantering in Rotterdam's waterway, is one of the largest moving structures on Earth. Its two curved steel arms, each the length of the Eiffel Tower laid on its side, swing closed across the shipping channel. Automatically, when storm surge forecasts exceed a defined threshold, the system was designed to protect against a storm that occurs statistically once every 10,000 years. If Valeria maintains its current track and intensity, the warning to landfall window for the Tampa region is currently projected at between 48 and 72 hours. Subtracting 42 hours for evacuation means the evacuation order for Pinellas. Highest risk residents would need to be issued within the next 6 to 30 hours of that window opening. Every hour of hesitation costs evacuation capacity. Dr. Collins stated in the May 2026 publication summary, the Tampa Bay region has the exposure of a major coastal city, the geography of a storm surge amplifier, and the evacuation constraints of a peninsula. A direct or near-direct major hurricane hit would test every assumption built into current emergency management plans. The community needs to be under no illusions about what that scenario looks like on the ground. The city of Tampa and Hillsborough County have made real progress on public hurricane awareness. Evacuation zone maps have been updated and distributed. Shake Alert's weather equivalent, the National Weather Service's wireless emergency alert system, is operational, but the volume of coastal real estate development that has occurred in the Tampa Bay region over the past 2 decades means more people and more structures are now inside the highest risk storm surge zones than at any previous point in Tampa's history. When you lay all of this out, Valeria intensifying by 95 miles per hour in 36 hours in the Atlantic, Super Typhoon Haemong bearing down on the Philippines in the Pacific, record Gulf of Mexico sea surface temperatures. Published by NOAA this week, in the Arabian Sea generating its 3rd cyclone of the 2026 season. The natural human instinct is to ask, is this normal? Is the planet becoming more stormy? The honest scientific answer is nuanced, and it is worth understanding precisely. Tropical cyclones, hurricanes, typhoons, and cyclones are the same meteorological phenomenon, named differently by ocean basin form, and intensify the same way, regardless of what basin they are in. Warm ocean water, atmospheric instability, low wind shear. These conditions exist across the tropics every year. The planet generates between 80 and 90 named tropical cyclones per year, globally, in a typical year. The total number of storms has not changed dramatically in the observational record. What has changed is where the energy is going. Research published in the Proceedings of the National Academy of Sciences by Dr. James Cosin, formerly of NOAA's Cooperative Institute for Meteorological Satellite Studies, analyzed global tropical cyclone intensity trends across 4 decades of satellite data, finding the proportion of storms reaching major intensity category 3 and above has increased globally. Storms are not becoming more frequent, they are becoming more powerful when they form, and critically, they are intensifying faster. The rapid intensification of Valeria has just undergone, 95 miles per hour in 36 hours, was once considered a rare, extreme outlier. NOAA data shows that events classified as rapid intensification have become measurably more common in the Atlantic Basin since 2000. The physical driver is straightforward. Rapid intensification is fundamentally limited by ocean heat content. Warmer, deeper warm water layers allow a storm to continue extracting energy even as it stirs up cooler water from depth beneath it. When the warm layer is thin, a storm's own churning can cut off its fuel source. When the warm layer is deep, as Gulf of Mexico and Atlantic SSTs have been making it in recent seasons, that's self-limiting. Mechanism weakens. NOAA's 2026 Atlantic hurricane season forecast, published in June, projected an above-normal season, 18 to 22 named storms, 9 to 13 hurricanes, 4 to 7 major hurricanes. The agency cited record warm Atlantic and Gulf Sea surface temperatures, and a La Niña climate pattern, which suppresses Atlantic wind shear and historically correlates with more active hurricane seasons. Valeria is the fourth named Atlantic storm of the 2026 season. It is July 30th, but the peak Atlantic hurricane season runs from August through October. The planet's storm-generating machinery is not malfunctioning. It is doing precisely what the physics of a warming ocean predicts. What changed is not the frequency of storms. What changed is the energy available to each storm that forms. And what that means for the cities sitting in their paths. Let us be direct about the practical message here, because information without action is just anxiety. The Netherlands proved that catastrophic coastal flooding is an engineering problem. With engineering solutions, if the political will to fund those solutions exists, the gap between New Orleans in 2005 and the Netherlands in 2005 was not geological bad luck. It was 52 years of sustained investment versus 52 years of deferred maintenance and underfunded levees. The death toll was written before the storm formed. Here's what you can control today if you live in a hurricane vulnerable zone, which means the Gulf Coast, the Atlantic seaboard from Florida through the Carolinas, and any coastal area within reach of a landfalling tropical cyclone. Know your evacuation zone. Not approximately. Exactly. Go to your county's official emergency management website today and look up your address. Every Gulf and Atlantic coastal county maintains an official zone designation. Zone A is highest. Risk. Zone B is next. If you are in Zone A or Zone B and a Category 3 or higher hurricane is tracking toward your area, you leave. Not when the order is issued before, because by the time the mandatory evacuation order is in effect, the roads are already filling. Have 72 hours of emergency supplies in a portable form, meaning supplies you can load into a vehicle in under 10 minutes, food, water, medications, important documents in a waterproof container, phone chargers, first aid kit, cash. A hurricane that requires evacuation may also mean you cannot access ATMs or card readers for days after landfall. If you choose to shelter in place in a non-evacuation zone, stay on an upper floor during the storm. The cause of death in the vast majority of direct hurricane fatalities is drowning from storm surge, not wind. Storm surge water rises fast and can trap people on ground floors who believe they were safe because their structure appeared sound. Know your county's emergency alert system and make sure wireless emergency alerts are enabled on your phone. The National Weather Service issues watches and warnings with specific timing. A hurricane warning means hurricane force winds are expected within 36 hours. That is your preparation window. If you are waiting for that alert to begin packing, you have already waited too long. And for coastal residents, understand the difference between storm surge and flooding. Flooding is rain-driven water that rises gradually. Storm surge is ocean water that arrives as a wall pushed by the prowl, storm's onshore winds, and can rise 5, 10, or 20 feet in hours. It is the mechanism that killed 90% of Katrina's victims and accounts for roughly half of all direct hurricane deaths in the American historical record. These preparations take one afternoon against a storm that the Gulf of Mexico is currently building into a system capable of catastrophic damage. The math is not complicated. Final thought. Hurricanes have formed in the Atlantic Ocean every year for millions of years, long before any European explorer crossed that ocean, long before New Orleans was founded below sea level, long before Tampa was a city of 3.3 million people built along a funnel-shaped bay. The thermodynamics that produce tropical cyclones. Warm water, an unstable atmosphere, the Coriolis effect from Earth's rotation are as permanent a feature of this planet as the ocean itself. We have no ability to stop a hurricane from forming. We have no technology that can reduce its wind speed or redirect its track with certainty. What we have is 48 to 72 hours of warning, increasingly accurate track forecasting, and the infrastructure and individual choices we made before the storm began to organize. The Netherlands made its choice after 1,836 people died in 1953. They spent 44 years and billions of dollars and built a system so reliable that the country has been effectively removed from the category of places that suffer catastrophic hour. Coastal flood disasters. That is not a small achievement. It is a demonstration of what sustained commitment to a known risk looks like when it is taken seriously. New Orleans showed what happens when the risk is acknowledged but the investment is deferred, when the levees are designed for a Category 3 but not maintained to that standard. when the evacuation options available to lower-income residents are insufficient, when 1,833 people pay with their lives for decisions made over decades by people who had already moved on by the time the storm arrived. Valeria is forming right now. The Gulf of Mexico sea surface temperatures are at a 172-year record for this point in the season. The loop current is running at full strength. A Category 4 or 5 storm hitting a major Gulf city in 2026 is not a hypothetical. It is a scenario that every emergency management agency from Houston to Tampa is running models on this week. What happens when it makes landfall will depend on decisions being made right now in emergency management offices, in governor's mansions, in county evacuation planning meetings, and in the individual households that decide tonight whether they are prepared to leave, stay, or simply hope. We will keep tracking Valeria and every system behind it. Subscribe so you do not miss updates as this develops, and leave that comment below. Have you ridden out a major hurricane? Tell me, where, what category, and what the worst hour felt like. Because these are not just meteorological events, they are human experiences. And understanding that is how we stay motivated to take them seriously. The Saffir-Simpson hurricane wind scale, the Category 1 through 5 classification system used by NOAA and displayed on every television weather map during hurricane season, is useful. It is also widely misunderstood in the way people use it to assess their personal risk. The first misunderstanding is the relationship between category and damage. The scale is not linear. A Category 4 hurricane does not cause approximately twice as much damage as a Category 2. The relationship between wind speed and structural damage is closer to a cube function, meaning that doubling wind speed produces roughly 8 times more destructive pressure on a structure. The jump from 100 miles per hour to 130 miles per hour of sustained wind is, in terms of physical force on a building, an enormous difference. Consider the numbers directly. A Category 1 hurricane at 80 miles per hour exerts a dynamic pressure on a wall surface of approximately 20 pounds per square foot. A Category 4 at 150 miles per hour exerts over 55 pounds per square foot on the same wall. At Category 5 levels, a door or window that fails creates a pressure differential inside the structure that can push a roof off from the inside, not from wind pulling it from above. This is why the building failure mode in Category 5 events is often not the windward wall blowing in, but the leeward side of the roof lifting off as interior pressure drives it outward. The second misunderstanding is more dangerous. The belief that category predicts personal risk with sufficient precision for individual decision-making. It does not. Category measures wind. It does not measure storm surge. It does not measure rainfall. It does not measure the storm size. It does not measure whether the geography of your specific location amplifies surge the way Tampa Bay amplifies it. Hurricane Katrina made landfall as a Category 3 storm. Most of the people it killed drowned in storm surge, not wind. The person in a solid reinforced concrete structure 15 miles inland might survive a Category 5 wind event with limited injury. A person in a wood frame structure at a 4-foot elevation 2 miles from the coast of Tampa Bay might drown in a Category 2 storm that produces catastrophic surge. The category is a headline number. Surge maps, flood zones, and elevation data are what determine personal risk, and those maps are publicly available from every Gulf and Atlantic coastal county's emergency management office. Storm surge is responsible for approximately 49% of all direct hurricane-related deaths in United States history. It is the dominant killer in major landfalling events, and it is the least understood hazard of the 3 primary hurricanes. Threats: wind, surge, and rainfall among the general public. Here's the physics of what storm surge actually is. When a hurricane's powerful onshore winds blow across the ocean surface toward a coastline, they pile water up. The storm's low barometric pressure also contributes to the atmospheric pressure. Near the center is so low that it allows the ocean surface to dome upward beneath the eye, like water rising inside a drinking straw when you place your finger over the top. The combination of wind-driven water and pressure-induced oceanic rise produces a broad dome of elevated ocean water that travels with the storm and arrives at the coastline at the moment of landfall. This dome of water, the storm surge, arrives not as a wave, but as a rapid, sustained rise in sea level. Unlike a tsunami, which arrives in distinct visible waves separated by troughs, storm surge rises continuously and does not recede quickly. In a major storm, the surge can rise 3 to 5 feet per hour, which means water that is ankle deep when a person decides to shelter in place can be chest deep an hour later and above. Roofline level 4. Hours after that, the 1,900 Galveston hurricane remains the deadliest natural disaster in American history. 8,000 people killed. The cause: a storm surge that covered the entire island of Galveston, Texas, with water. The island's highest natural elevation was 8.7 feet above sea level, and the storm surge was 15 feet. For the current Valeria scenario, NOAA's storm surge unit is currently modeling surge values for the Gulf Coast based on ensemble track forecasts. At the center of the projected impact zone, the highest probability landfall area for the current forecast cone, preliminary modeling places maximum surge values between 12 and 18 feet for a Category 4 landfall and 18 to 25 feet for a Category 5 landfall, maintaining current intensity. 25 feet of storm surge means a two-story house at sea level has its second floor submerged. It means vehicles floating through streets. It means anyone who waited to evacuate and is on the ground floor of the wood frame structure when the surge arrives is in severe and immediate danger. The areas most at risk in any Gulf landfall are not the areas with the strongest structures. They are the areas with the lowest elevation and the least time between shoreline and inhabited neighborhoods. And in the Tampa Bay funnel-shaped geometry, the mathematical amplification of those numbers is significant. The science of hurricane track forecasting has advanced dramatically over the past 30 years. The 5-day track forecast that NOAA's National Hurricane Center routinely publishes today is more accurate than the 3-day. Track forecast was in the 1990s